the idea here is it's very similar to what we did in the two-variable situation. All right, so here we have a coordinate system u, v, w. I had it like this. So I had the new coordinates on the left and the Cartesian coordinates on the right. Okay. So suppose we take in the new coordinates a volume, a little chunk of volume. So that represents dv. All right. And now when I move that over, in these coordinates it looks like a cube, but in the Cartesian coordinates it might look like something different. It might be kind of a curvy thing. So it's not a cube anymore. So what we want to do is we want to figure out, how does that volume change? How does the volume change when I move from this cube and these coordinates to this funny distorted cube in the new coordinates? All right. So what we did last time is we looked at where these vectors went, the vectors that define the edge of the cube. Well, they go to new vectors over here. Now, if their lengths get expanded, then that expands the volume. Okay, so we want to explore exactly how that happens. And we talked in that video, I talked about how there's a function that transforms us from this set of coordinates to this set of coordinates. And so each one of these coordinates, x, y, and z, are functions of u, v, and w. So given a u, v, w, I know what my new x, y, z is. Okay, so what we want to do is we might know what the volume of this is. What we want to do is find out what the volume of this is. This is, this three-dimensional thing is a parallelepiped. Right? So if I look at the three vectors that defined this cube, that's a parallelepiped that happens to be all the vectors are at right angles. When they come into these coordinates, they may not be at right angles to each other anymore. Right? So what we want to do is we want to find the volume of that parallelepiped. This vector, the vector that it turns into, is called fu du. It's the u derivative of f multiplied by the du, a small change in u. And this vector over here is f. That would be the one that the w direction went to. So that would be fw dw. And the one in the back here, that's oh, actually that was the fu du. The one in the front here is v dv. So these three vectors, du's in the back, dv is over here, and dw over here, get transformed to this. All right. So the new volume in these coordinates, what it's going to be, is it's going to be the volume of this parallelepiped. And if you remember from early on in the course, we talked about how to compute the volume of a parallelepiped. You take one vector and dot it with the cross product of the other two. All right. So I'm going to take, say, fu du, and I'm going to dot it with the cross product of the other two vectors. All right. Now, these things are just scalars, so they just come out front. So I just take fu dotted with fv cross fw, and then I've got du, dv, dw out here. And that's going to be my volume element, and this is going to be my Jacobian. So this thing here, and I'm actually going to put it in, this is a volume, so you have to take the absolute value, right? So this thing here is the Jacobian. Okay. Now, what are these things? How do you compute these? Well, remember, f has three components. It's determining an x, y, and a z. So f is just the function, it's x, y, and z, right? Where x, y, and z are all functions of u, v, and w. So when I compute fu, I'm getting the u derivative of x, the u derivative of y, and the u derivative of z. And when I compute fv, I'm getting the v derivative of x, the v derivative of y, and the v derivative of z. And when I compute fw, I'm getting the w derivative of x, the w derivative of y, and the w derivative of z. So these are the three vectors that I'm doing this to. So it's similar to the last problem. Oh, there it is underneath, where the Jacobian was this, xuYv minus xvyu. Now it's going to be this, where you plug these vectors in for these places here. So it's a little bit more complex, all right? But it's the same idea. I want to just do an example in spherical coordinates, all right? What if the UVW that we were going to were the spherical coordinates, rho, theta, and phi? What happens? Okay, so I set this up in Maple. So you should be seeing my Maple screen here. And so I just defined x, y, and z in terms of what we know they're defined by. This is the change of coordinates that you need to do to go over to spherical coordinates. Okay, so if I just define x, y, and z in their spherical coordinates like this, so this is the transformation. This defines that function f. F is the vector that consists of these as its components, right? Now, what I need to do is I need to compute Fu, Fv, and Fw. Well, in this case, it's F rho, F theta, and Fv. So maybe that's what I should have called these. This is F rho. So let's define that like that. This is F theta, so I'm differentiating everything with respect to theta here. Where's my theta? There it is. And this is F phi. Okay, so I've got those three vectors. I took the rho derivatives, the theta derivatives, and the phi derivatives. And now the Jacobian is going to be one of these dotted with the cross product of the other two. So let's take this one and take the dot product of, I'm going to take the cross product of the other two. So let's put this in here, and we'll do a cross product. So I need the cross product symbol. There we go. And waboom. Okay, that's ugly, but Maple can simplify. Simplify the last result. Look at that. It's rho squared, it's negative rho squared sine phi. Remember though, we're taking the absolute value of this, right? So when you take the absolute value, you get rho squared sine phi. That's exactly what, if you recall from spherical coordinates, that's exactly what happens when you go from x, dx, dy, dz to d rho, d theta, d phi, you've got to multiply by rho squared sine phi. That's where that comes from. That's the Jacobian, all right? Okay, so I've got this triple integral. Sorry, it was a little messy writing it down. And we want to evaluate this. We could do it by like as it is, but let's do the change of variables. Well, remember, we need to compute that Jacobian, and the Jacobian is the derivative of x with respect to u and derivatives of x's, y's, and z's with respect to u's, v's, and w's. So we need to solve this stuff for x, y, and z. This set of equations is not too bad. Z is really easy to get, right? Z is just, you just multiply both sides by 2 here. You get z equals 2w. Not too bad. Y is pretty easy to get. You just, y is equal to, just divide both sides by 3. It's just v over 3. And this one, well, this is a little more complicated. I can solve this for x. X is u plus z. But what is z? Z we said was 2w. So that's u plus 2w. So here's my formulas for x, y, and z. Okay, so to compute the Jacobian, we're going to need to compute the derivatives. So we need to find xu, xv, and xw. We're going to need to find yu, yv, and yw. And we're going to need to find zu, zv, and zw. Okay. xu, that's the derivative of x with respect to u, that's 1. xv, the derivative with respect to v, there's no v here, so the derivative is 0. xw is 2. Right? Just looking at this expression and just differentiating with respect to these different variables. These are partial derivatives. Okay, let's look at y. yu, well, there's no u's here, so it's 0. yv, well, that's just a constant that we're multiplying by, so that's just 1/3. yw, there's no w here, so it's 0. Zu, there's no u here, so it's 0. Zv, there's no v, so it's 0. Zw is 2. Not too bad, right? So when we go and do the Jacobian, remember the Jacobian here is going to be the absolute value of fu dotted with fv cross fw, okay? Fu is the vector, this is fu, it's the vector 1, 0, 0. Fv is the vector, the xyz's with respect to v. And Fw is the derivatives with respect to w. Okay, so Fv cross F, oop, my screen seemed to froze. Okay, it's back. I'm just crossing these two vectors. Okay, so what's the cross product here? Well, just ignore the first row here. It's this times this minus this times this. Right, so it's 2/3. Comma. Then I ignore this one. I do the negative of this times this minus this times this. Well, that's 0, right? And then cover up this. It's this times this minus this times this. So it's negative 2/3. So that's Fv cross Fw. What's Fu? So this is 1, 0, 0. All right, so I just have to dot these. Well, this is super easy, right? Because the dot product is just 2/3, right? Absolute value is 2/3. So my Jacobian in this case is 2/3. The Jacobian ended up being a constant. It's not always going to be a constant, but in this case it is. Okay, so what we have to do is now rewrite everything in terms of these new variables and then multiply by that 2/3. Well, what does y plus 1 become? Well, y is v over 3. So y plus 1 becomes v over 3 plus 1. Okay, so my integral becomes v over 3 plus 1. And then we have to multiply by the Jacobian, which we just found, multiplied by 2/3. And then we have to figure out whether we do du, dv, dw, or dw, dv, du, you know, what order we do these in. And to decide that, I think we need to see the picture of the region we're integrating over. So let's get an idea of what this region looks like in new coordinates. Let's see what it looked like in the original coordinates. The original coordinates for, let's see, z was ranging between 0 and 1. So from here to here. Y was going from 1 to 2. And then x was going from z to z plus 1. So z is that diagonal line, x, z equals x here. X equals z is just this. X equals z plus 1, that's the same thing as z equals x equals z plus 1 is the same thing as z equals x minus 1. So that's another line that just has an intercept down here at -1 on the z-axis. So x is going between these two lines over here. I'm drawing two lines in the xz plane. So it looks like what I'm getting here, if I come out from z equals 1 in this direction, I'm getting this kind of shape. So it's that shape, but over here. So it's kind of like a it's one of these. This is the region that I'm integrating over. It's a parallelepiped. when I change coordinates, what happens? So what does that picture become down here for U, V, and W? Well, let's see. Let's start with Z again. Z goes from 0 to 1, right? So that's the height of this thing. And W is Z over 2. So W is just going from 0 to 1/2. All right, so W goes from 0 to 1/2. Y went from 1 to 2, right? That's this part. And V is just 3Y. So V went from 3 to 6. So on the V axis, I went from 3 to 6. And then X went from Z to Z plus 1. Well, that's the one that's a little bit trickier. So when I say X equals Z, what is that? Let me get a new sheet here. When I say X equals Z, what is that in the new coordinates? Well, Z is the same as 2W. X is the same as U plus 2W, right? So if I solve this for U, I say this equation is just U equals 0, right? So the lower bound, so the X equals Z, the lower bound of my inner integral just becomes U equals 0 here. So we start here, okay? And then the upper bound of that inner integral was X equals Z plus 1. Well, X, as I said, was U plus 2W, and Z is 2W. So if I subtract 2W from both sides, I can simplify this to just U equals 1. So U just goes from 0 to 1. This is fantastic. See what I got? I just got a box. It's still a parallelepiped, but now it's a very special parallelepiped. It's just a parallelepiped with all right angles. So actually, I can set this up du, dv, dw, dv, du, dw. I mean, it doesn't matter what order I do it in whenever I have a rectangular region. U goes from 0 to 1, V goes from 3 to 6, and W goes from 0 to 1/2. I didn't really need to draw the original picture, but I think it's useful to do that just to get a handle on what's going on. And that's an integral you can totally do. I'm just going to pump it into Maple here, since we know how to do these kinds of integrals. So we had 0 to 1/2, 3 to 6, and 0 to 1. The integrand became V over 3 plus 1 multiplied by our Jacobian. Don't forget that. Okay, Maple wants to write it like this, whatever. du, dv, dw. There we have it, 5/2. Okay, equals 5/2.